Mr. Tarrou, in this lesson we are going to continue our work of solving separable differential equations. It's the second video I've done on this, so I'm going to reintroduce the definition a little bit and do three more examples that are a little bit more complicated than I did in my previous video. Separable differential equations, again, is a differential equation of the form dy dx is equal to f of y times g of x. And if we can rewrite that in this particular case the way the definition is written by dividing both sides by f of y and moving our dx over to the other side. Once we separate our two variables of interest, we will be integrating, finding the indefinite integral of both sides of our equation and with respect to whatever that isolated variable is. So over here we have solve y times y prime is equal to -4 times the sine of pi x. Well, that's going to be, just to kind of, this notation's nice, but for the purposes of these types of problems, I'm going to rewrite that as dy dx, and that's equal to -4 sine of pi x. Excuse me. And now it's a little bit clearer to see what we have to do to separate the variables. We already actually have a y with the dy, but we have a derivative with respect to x here, and our x is on the other side of the equation, so we're going to rewrite that as y dy is equal to -4 sine of pi x dx. And now we're going to take the indefinite integral of both sides with respect to, again, its isolated variable. So let's just introduce that. And a couple things here. Well, the left side's basically ready to go, but the right-hand side, you can do your integration with recognizing of a pattern or using a u substitution. And for the first example here, I'm going to do a u substitution and show it a little bit differently in my next example. We have an inside function here inside the sine, so I believe that we can go ahead and let u equal pi x, and then du is going to be equal to pi dx. Well, see, we have a -4 out front. We're going to move that constant in front of our integral symbol here, and that would just leave us with a coefficient of x and not a coefficient of pi x. So if I were doing, if I was integrating by recognizing the pattern, more general pattern, then maybe I could show a multiplication of pi, so I would exactly get that pattern set up correctly, and then have a division of pi out front. But for the purposes of this problem, I'm going to divide both sides by pi and get 1 over pi du is equal to dx. And with these little substitutions on the side, these formulas set up for our u substitution on the side, I can get my problem to exactly match my more basic integration rule for sine and not do a whole derivative of the inside function pattern. So let's get the dogs calmed down and get this next line. Oh, all right. Maybe they won't be too bad. So sorry about that. We got the indefinite integral of y dy. We're going to let that -4 come out front along with that division of pi, or that multiplication of 1 over pi. Excuse me. And actually, you know, I'm starting my u substitution here. I've got that 1 over pi out front, but that 1 over pi is coming out there so that I have a 1 over pi du is going to replace our dx, which is right here, and I've already moved my -4 out front. So I'm going to go ahead and add my du here. And then we have the sine of pi x. Well, that can be written as sine of u. And I'm debating whether to stop the video. I'm going to call my dog down here. The indefinite integral of y dy is going to be y squared. And we've raised that power by 1 through the integration process. Now I have to divide by that. So I'm going to have that 1/2 out front. And then over here we've got equals -4 over pi. And the indefinite integral of sine, let's see here, the derivative of sine is cosine, the derivative of cosine is negative sine, right? So it's going to be negative cosine of u plus c. Now, getting this cleaned up and getting the problem, because with the indefinite integration, we need to go back to the original variable, right? So we have 1/2 y squared is equal to negative times negative is positive, so 4 pi cosine of pi x plus c. And that's solved. I guess, we could maybe multiply both sides by 2 and square root both sides if we really needed to, depending on the format of the answer that your teacher was concerned with. I think it's bothered me a little bit, and even on my notes I did multiply both sides by 2. But I'm going to end with y squared is equal to 8 over pi cosine of pi x plus c. And just to make sure, excellent. All right. Next example. Find the particular solution to the differential equation 4y times 2 plus x squared times y prime, and this is these are all derivatives with respect to x, so that would be dy over dx, minus x times 1 plus 4y squared plus 0. And we are, in this one, going to be looking for a particular solution, so we need some extra information given, and that will be y of square root of 6 is equal to the square root of 7 over 2. Now, with my calculus class, I'm only going to be needing to cover, at this point, the separable differential equations, so hopefully we can manipulate this to get all the variables of x and y separated on opposite sides. So, this has an x factor and something going on here with y as well, but for now, let's just get that over to the other side of the equation. We're going to add that to both sides, and we get, I guess maybe I'll start writing here, 4y times 2 plus x squared dy dx, to instead of that y prime, to more easily see the separation of variables we need to create. Add that to both sides and we get x times 1 plus 4y squared, and that's it. Okay, we're going to do a couple of things in this next step. We're going to take this denominator, if you will, this isn't exactly division, but we're going to move this dx over to the other side. We're going to divide both sides by 2 plus x squared, and we're also going to divide both sides by 1 plus 4y squared. So, what do we have here? We have 4y. We're going to bring this over to the other side, the left side of our equation through division. Excuse me. Over 1 plus 4y squared dy. Kind of doing, obviously, a few things here at once. Now we've got our x, and we're going to bring this over with division to separate that multiplication. So we'll have x over 2 plus x squared. And again, we're going to move this dx over to the right-hand side of our equation. And yeah, we were able to separate our variables. Once we do that again, we take the indefinite integral of both sides of our equation in respect to, or with respect to, our isolated variable. And because this equation now has a couple of integrals and they're not too terribly difficult to integrate, I'm going to set them up to match sort of the pattern of the integration rules, as opposed to like where you have the u substitution, if you will, already kind of thing. And so I don't want to do a u substitution on both sides and make it like a u substitution over here and a w substitution over here to make each side perfectly match the integration rule. Because what I'm looking at here is we have an exponent of 2 in the denominator and an exponent or power of 2 of 1 in the numerator. So, when you take the derivatives using the power rule, those exponents decrease by 1. So it does look like the numerator is possibly a derivative of the denominator, and that's that du over u pattern I'm thinking of, trying to make this match for finding that our answer is going to be the natural log of u, absolute value of u. Well, the derivative of 1 plus, I can write this over here for a second, u is equal to 1 plus 4y squared. Well, then du would be 8y, or the derivative of, the derivative of u with respect to y would be 8y. So if that were 8y, then I would match that du over u pattern, and I would be able to, basically be done and do my integration. So if I can multiply that numerator by 2, but then to cancel out that multiplication of 2, I would need to divide by 2, like finding common denominators, right? So we're going to multiply, we're going to introduce a multiplication of 2 and a division of 2, so that effectively multiplying by 1. And the same thing over here, the derivative of 2 plus x squared is 2x. So if the numerator was 2x, then the numerator would be the derivative of the denominator. We would have du over u. So I'm going to slip in a multiplication of 2 and a division of 2 out front, and we have 1/2, in a broken piece of chalk, we have 1/2 times the indefinite integral of 8y over 1 plus 4y squared dy is equal to 1/2 times the indefinite integral of 2x over 2 plus x squared dx. Now, I can, both sides, left and right hand side of my equation, one term, and there's a multiplication of just 1/2 in front of each of those. So I can now take this entire equation, if I want to continue to make this appear as simple as possible, and multiply both sides of the equation by 2. And that will give me the indefinite integral of 8y over 1 plus 4y squared dy is equal to the indefinite integral of 2x over 2 plus x squared dx. And now, du, u, du, u, we end up with the left side being the natural log of the absolute value of 1 plus 4y squared, but really those absolute value symbols are not necessary because that's an addition of 2 positive terms, so there's no way that this can be negative. That's an even power, so no matter what y is, that's going to be a positive expression. So that's not really necessary, and we can just write the natural log of 1 plus 4y squared. And on the right-hand side, we have the natural log, again, positive. We're adding, and we have an even power, so that's always going to be positive. And then, of course, we're doing indefinite integration, so don't forget that constant of integration. Now, we're done with the integration, but, and, you know, if this is an open, like, say, an open-ended question on the AP exam, if that's even would be this type of question, you don't get points for simplifying, but if this were multiple choice, I doubt we would see an answer like this, or if your teacher is expecting you to simplify both sides of the, simplify your answer, we can get this a little bit cleaned up. Make both sides an exponent of e to cancel out that natural log function, or that log base e, and we get 1 plus 4y squared. Now, I wrapped the right-hand side in a set of parentheses because, well, there's 2 terms there, not just 1. So it's not just going to be the e, the exponential function, base e, and log base e are just going to cancel out. We have the e now raised to 2 things being added together. When you add exponents, when you multiply like bases. So this becomes e to the c power times e to the natural log of 2 plus x squared. E to any arbitrary constant is going to be another arbitrary constant, so that's going to be 1 plus 4y squared is equal to c sub. Really should argue that you should put a little subscript there to show that this constant's not really the same value as that unknown constant. And now the base e and the log base e are going to cancel out, and we get 2 plus x squared. 2 terms there, so don't forget your parentheses. Subtract both sides by 1. Divide both sides by 4 if we really need to do that, and we'll get y squared is equal to c sub 1 divided by 4 times 2 plus x squared minus 1/4, and that is the end of my second example. Let me check my notes. We're looking good. All right, one last example. Coming right up. Since you keep hearing them in this particular video, this is the 2 pluff balls that you keep hearing. This is Theodore, he's 11. This is Wally, he's 2. And these are our kids. Since I teach, I get to come home to 4-legged kids instead of 2. Anyway, they're Pomeranian toy poodle mixes, and they're making sure that I know that something's going on outside. Well, okay, I said we were going on to our next example because, well, I was distracted, but now that I'm not, we only found the general solution. We want to find the solution that, you know, has a value of square root of 7 over 2 when x is equal to the square root of 6. So we're just going to plug these values into our answer and find our constant. So, y squared, so we have, let me just make sure I wrote this right, yes. So we have the square, or let's write over here so I have some more room. We have square root of 7 over 2 squared is equal to 1/4 c, so 1 if you will, times 2 plus our x value is square root of 6. Let's see, that's supposed to be squared minus 1/4. Alright, well of course I try to make this, you know, work out relatively easily, so we have square root of 7 squared is 7 over 4 is equal to, now what do we got going on here? The square root of 6 squared is just 6, and 6 plus 2 is 8, and 8 divided by 4 is 2. I'm going to leave off that subscript. Minus 1/4. Of course, when you add both sides by 1/4, you're going to have 7 over 4 plus 1 over 4, which is 8 over 4, or 2. So 2 is equal to 2c. That means that 1 is equal to c. And that means our particular solution is y squared is equal to 1/4, well, c is just 1, times 2 plus x squared minus 1/4, and I don't believe I made any mistakes, at least I match in my notes. Let's get on to that last example. Bam! Last example. We got dy over dx is equal to e to the 2y minus x. Alrighty then, let's see. How are we going to separate these variables? Because both of our variables, x and y, are in the same exponent. Well, when do you subtract exponents? Right? When you divide like bases. So that is means that we're going to be able to get some white chalk here, and we get dy over dx is equal to e to the 2y power divided by e to the x. Now we're going to move our dx over to the right and multiply both sides by e to the, oh no, no we're not. No we're not. No, we're not going to do that. We are going to, we're going to divide both sides by e to the 2y power and get 1 over e to the 2y dy, and then we're going to move the dx over to the other side. Now this ex is in the denominator, and don't let it magically float up because you have moved or divided both sides of our equation by e to the 2y power. It's staying down there, so it's going to be 1 over e to the x dx. Alright, well now we have isolated both our variables on, you know, each side of our equation. We're going to take the indefinite integral of both sides with respect to the isolated variable. Well, we're not quite set up to just write the answer, so this is going to be e to the negative 2y, just to make it look a little bit cleaner for what I prefer. And over here, we're going to have the indefinite integral of, leaving some room for some stuff I'm going to have to add in here, e to the negative x dx. Now, we can do some u substitutions, or do like a u substitution over here and a w substitution over here, like I've done in some other videos where I like to do my u substitution to the point where I get my problem to exactly match those basic integration rules. But again, I'm trying to get to more in the habit of, and showing you both ways, where you start to recognize the pattern as well. In other words, if you looked at this and said, well, that's not just e to the x, I need to do a u substitution. Well, u is going to be, hopefully, negative 2y, and then du would be equal to negative 2. Now we're taking the integral with respect to y, so it'll be negative 2 dy. and you're like, what I have, I have a 1 dy, and I would normally divide both sides by -2 and da-da-da-da-da. But basically, if I had a -2 here, I'd have my -2 dy, and I'd be getting, fitting and recognizing that pattern so that we can finish our integration problem. So I'm going to go ahead and introduce that multiplication of -2 here and create that -2 dy that we have here. But then I need to counteract that, so we'll have a multiplication or division of -2, or multiplication of 1 over -2 out front. And over here, same thing, it's not just a basic exponent of x, it's -x. So again, with that u substitution, if I were to let u equal -x, then du would be -1 dx. Oh, I need -1 here. And then to counteract the fact that I just added in a coefficient of -1 to match that integration rule, then I need to counteract that with a division of -1 out front. But I'm going to show us that, dividing by 1 and multiplying by 1 appear to be the same thing because it's the identity of addition and multiplication and division. Well, now I'm matching that sort of like du, or u prime, e to the u pattern, so I can write my integration here and go, well, this is going to be -1/2. The integral of e to the x is e to the x plus c, right? So we're going to have -1/2 times e to the -2y. And then on the right-hand side, we have negative. This is going to be, with that u and that u prime there, is going to be negative, what? Negative e to the -x plus c. And let me just check my notes. Make sure I didn't say something silly. Okay, now we can multiply both sides by either 2 or -2, and if we just multiplied by 2, then we would have negative e to the -2y is equal to -2. There's really no reason to do this, maybe, except for just write it to look a little bit differently. E to the -x plus c. Well, you can even argue that that's supposed to be a different c because you multiplied by 2, but at any rate. If there's any doubt about, you're trying to set up your integrations to match this this u substitution pattern as opposed to doing u substitution to get your problems to exactly match those basic rules, you can always take the derivative of this to make sure it matches this, right? The derivative of what? The derivative of, well, I'll be looking here, the derivative of e to the u is e to the u times u prime. Well, the derivative of e to the u would be e to the u times u prime. That would be, -2, which would cancel out with the multiplication of -1/2 and get us right back to where we started from, so it would check out okay. And this is our general solution to this differential equation. But I gave us some extra information again to find the particular solution, so we're going to plug in those values of x and y and get negative e to the -2 times 0 power, kind of purposely made this work out so it wasn't going to be too terribly difficult, times equals -2 times e to the -0 power plus c. Of course, anything to the 0 power is equal to 1, so it's going to be -1 is equal to -2 times 1 plus c. Adding 2 to both sides, we get 1 is equal to c. And our particular solution is going to be negative e to the -2y power is equal to -2 times e to the -x power plus 1. And just to make sure we've got a match to my notes, we are good. And that is the end of my third and last example. I'm Mr. True. Bam! Go do your homework.